Hello students. In this video, let us discuss about the quantum mechanics part 2. So part 1 already I did. Now part 2, here also we are talking about the formulas which will be asked in multiple choice questions. Okay. In that, the next formula, one-dimensional Gaussian wave packet. The propagation of Gaussian wave packet is written as the wave function psi x comma t equal to 0 is equal to 1 by pi sigma square whole to the power of 1 by 4, where sigma is the spatial width of wave packet. E to the power of minus of x minus x naught whole square by 2 sigma square e to the power of I by h cut p naught x, where x indicates the positions and p indicates the momentum. Okay, h cut value is h by 2 pi. Sigma is spatial width of wave packet. Right? Now wave function is normalized. Remember this. It may be asked as a bit. Now the expectation value, if these symbols comes, you think it as an expectation value. The expectation value of x is written as, in last video we wrote the expectation values. Okay. Now that is equal to minus infinity to plus infinity psi star x psi dx, which is equivalent to x naught. Psi is the wave function. Psi star, what we discussed, the complex conjugate of a wave function. And expectation value of x square is integral minus infinity to infinity psi star x square psi dx. In place of x, I substituted x square. Now that is equal to sigma square by 2 plus x naught square. Right? Now expectation value of momentum P. So here in place of x, we are substituting the momentum operator minus I h cut dou by dou x. Now here psi is there, no? So I wrote it as dou psi by dou x into dx is equal to p naught. Similarly, expectation value of p square, the same thing. I minus I h cut dou by dou x into I h cut dou by dou x. Right? So that value comes out to be integral minus infinity to infinity psi star. In place of x, I am substituting p square value. I minus h cut square dou square psi by dou x square dx. So if we simplify, we get h cut square by 2 sigma square plus p naught square. You see, the expectation value of x is x naught, p is p naught. You can remember in such a way. Here we substituted x. Here what we substituted? We substituted the operator of p, that is minus I h cut dou by dou. This we substituted or placed in place of x. Now see, expectation value of x square. In the place of x, we kept x square. Right? Now here minus h cut square dou square by dou x square. And see the value. Here you got sigma square by 2 plus x naught square. Here what you are getting, h cut square by 2 sigma square plus p naught square. Okay, these are the particular formulas for the expectation values related to the propagation of Gaussian wave packet. Now let us go for the Schrodinger equation 1 related one-dimensional consideration. Here we are discussing about the three conditions. The first one is orthogonality condition. So orthogonality condition is integral minus infinity to infinity psi n star psi n dx is equal to 0. Remember this important bits. Normalization condition, integral minus infinity to infinity psi n square dx is equal to 1. He will not ask the complete formula. How he will ask the question means, the normalization condition, integral minus infinity to infinity psi n square dx value is, he will ask whether 0 na 1 na. In such a way the options will be asked. Next, sometimes he may ask the formula also. Orthonormality condition. So orthonormality condition, here integral minus infinity to infinity. Okay, minus infinity to infinity psi x star psi n dx is equal to dou kn, right? Where k and n are the quantum states or which represents the wave function. Now here dou kn we call Kronecker delta function. So if dou kn is equal to 0, k is not equal to n. If dou kn equal to 1, k equal to 1. These conditions you have to remember. Kronecker delta. Now next, let us move for the particle in a one-dimensional infinitely deep potential well. So direct formula we are writing, the allowed energy levels are given as, you have to remember the formula at any cost. Most important formula which he asked in the exam. En equal to pi n square h cut square by 2m a square, where n integer 1, 2, 3. Okay. Now this En is written as, now in place of h cut we are substituting h by 2 pi, and if we simplify the energy level equation, most important, remember this equation, the energy level equation En equal to n square h square by 8 ma square. What is En? N square h square by 8 ma square. Okay. Now next, the lowest energy of a particle is obtained by putting n equal to 1. Now here in this equation, so it will be h square by 8 m a square. A is the width. Okay, A is the width of that particular dimensional potential well, infinite deep potential well. Okay, and now next, h as usual, Planck constant, m mass of the particle. Now here En. Okay, En, n square. Now what is h square by 8 ma square? Nothing but E1, no? So we can write En equal to n square E1. Now this is known as 0 point energy. So sometimes he asks the 0 point energy. 0 point energy is h square by 8 ma square or n square E1. Okay. Now next, the possible values of energy of the particle in the potential box are discrete, corresponding to 1, 2, 3. The energy is not continuous. In a simpler words, energy is discrete and the n values are 1, 2, 3. Now the spacing between the nth energy level and the next n plus 1 energy level, we will get as n plus 1 whole square E1 minus n square E1. So nth energy level, n plus 1 energy level, the next. If we simplify, we get 2n plus 1 E1. Okay, the spacing between the nth energy level and the next energy level is 2n plus 1 E1. And the corresponding eigenfunction, this is the most important another formula. You have to practice, you have to remember. Okay, so corresponding eigenfunctions are psi n is equal to under root 2 by a. A is the width. Under root 2 by a sin n pi by a x. Psi n equal to a wave function. Under root 2 by a sin n pi by a x. Right? Now next, the particle in a one-dimensional potential well of finite depth. Now before we discussed about the infinite deep potential well. Now one-dimensional potential well of finite depth. First, energy eigenvalues. 2p square pi square h cut square by 2ma square. P value 1, 2, 3, 4. V tends to infinity. V is the potential. If V0 is far greater than E, then E turns to be 2p plus 1 whole square pi square h cut square by 2m a square. Right? Now the linear harmonic oscillator. Now this is the most important formula for doing the problems also. The potential energy for this is V of x is equal to half m omega square x square. half m omega square x square. X represents position, omega represents angular frequency. Now the eigenvalues of energy E equal to n plus half h cut omega, where n equal to starts from 0, 1, 2, so on. If we substitute n equal to 0, we will get h cut omega by 2. Now this we call 0 point energy for linear harmonic. Right? You have to remember the 0 point energy for linear harmonic is h cut omega by 2. Right? The 0 point energy for deep potential well is h square by 8 m a square or n square even. Now next, for each n, we have the values of L ranging from 0 to n minus 1. Linear momentum. For each value of L, m values range from minus 1 to plus 1. Magnetic spin quantum number. And there are summation L equal to 0 to n minus 1, 2L plus 1 is equal to n squared states belonging to the particular energy. Now for ground state of hydrogen atom, the wave function is spherically symmetric. Remember, for ground state of hydrogen atom, the wave function is spherically symmetric. Right? Now next, psi 100 value is 1 by root 4 pi z by a naught whole to the power of 3 by 2 e to the power of minus z r by a naught, where r is the distance of nucleus. Okay, distance of a particle from the nucleus. Z, atomic number of nucleus. A naught as usual width. The probability of finding the electron. Here particle means here we are taking electron. Electron between r and r plus dr. R is the distance of the nucleus, I said, r and r plus dr. So we write as P of r dr equal to psi 100 whole square 4 pi r square dr, where this is equal to 4 z by a naught whole cube r square e to the power of minus 2 z r by a naught dr. The most important formula. He will ask in the bits the probability of finding the electron between r and r plus dr. This is the formula. What is the formula? 4 z by a naught whole cube r square e to the power of minus 2 z r by a naught dr. Next, let us go for the particle in a box, 3-dimensional. First, let us write the wave function related to this. Okay. The wave function is psi, nx, ny, nz. These are the 3 quantum numbers. Remember that quantum number never be equal to 0. Quantum number starts from 1 only. There will be no 0 quantum number. So nx, ny, nz in 3 dimensionals, the 3 different quantum numbers. Okay, 3 quantum numbers. The wave function for psi nx, ny, nz is 2 under root 2 by root abc sine nx pi x by a sine ny pi y by b sine nz pi z by c. Right? And now, the energy levels. How we will write? E nx ny nz is equal to h square by 8m. Most important formula, beta. So, he will ask in the MCQs. H square by 8m, n x square by a square plus n y square by b square plus n z square by c square. If a equal to b equal to c. Okay, let us discuss after this what will happen. First, let us write the energy states between E and E plus D. So that is 2 pi V, volume V is the 2m by h square, h Planck constant, m mass, whole to the power of 3 by 2, E 1 by 2. Right? Now, if particle is confined in a cubical box, in which A equal to B equal to C, how will be the formula? The formula turns to be under root 8 by a square, normalized wave function, under root 8 by a square sine nx pi x by a sine ny pi y by a sine nz by z by a. Instead of a, b, c, I wrote E. And eigenenergy value formula will be E nx ny nz equal to h square by 8 ma square nx square plus ny square plus nz square. Already I said no. There will be no zero quantum number. Quantum number starts from 1. If 0 is there, then what happens? What happens means the wave function will be 0. Wave function is 0 means particle does not exist. It will happen a no. So quantum number never be equal to 0. Now next, let us go for the energy levels. Okay, energy levels of particles in a cubical box. So these are important energy levels actually. So while preparing, pause the video and just write down these energy levels. Before discussing this, let us define what is degeneracy or degenerate energy levels. Degeneracy means two or more different quantum states have same energy levels. Okay, nx, ny, nz. In these three, two or more will have different states, will have same energy levels. Right? For example, let us see here, no? 2, 1, 1. Okay. So, I'm writing here, see, nx square plus ny square plus nz square. Our formula is this one. Right? Formula is this one. Now, 2, what I took? This excited state 1. For you to explain, I'm writing one example. Now, see. Here 2, 1, 1. The combination I wrote. See, 2 square plus 1 square plus 1 square. First combination. 4 plus 1 plus 1. 6. 1 square plus 2 square plus 1. 6. 1 square plus 1 square plus 2 square. What is 6? 6 only. Now here, two quantum numbers are different. Or one of the quantum number is different. No. 2 is there. One of the quantum number, here nx is 2, here ny is 2, here nz is 2, is different. Even though they are different, this combination if we take, we are getting the same energy levels, 6, 6, 6. Right? We are getting the same energy level. So this is 6 h square by 8 ma square. Or we can write 6 e. The value, this is nothing but equivalent to E. Okay, we can write it as 6E. Right? This we call degeneracy. If we have two or more quantum states of different values also, the energy levels will be same. Okay, they will have same energy levels. Similarly, non-degenerate. A state where each energy levels corresponds to only one unique state. 1, 1, 1. One unique state, 2, 2, 2. One unique state. Right? Here different. 3, 1, 1. 1, 3, 1. Right? 3, 1, 1, 3, 2. Different. But here same unique state. This we call non-degenerate. Right? Now here let us discuss about energy levels from ground state to excited state. So ground state. Right? Ground state, generally what we will take, this is nx, ny, nz. Okay? 1 only we will take, no? 1, 1, 1. 1 square plus 1 square plus 1 square is 3 square. Now only I wrote the formula, no? This formula only we are using. Now 1 square plus 1 square plus 1 square. Nothing but 3. 3 h square by 8 ma square. H square by 8 ma square is E. 3E I wrote. Now that this is the first excited state. Second, third, fourth, fifth, sixth. These all are the excited states. Up to 9 excited states. Right? Now, for the excited state, let us see the combination of quantum numbers. In the first excited state, I replaced one different quantum number. In 1, I wrote 2. Okay. Now, see the combination. Here already I explained, 2, 1, 1, 1, 2, 1, 1, 1, 2. So in these three sets, if we do nx square plus ny square plus nz square, this formula, energy formula, then we are getting 6 only. 6E I'm getting for these three combinations. So how many combinations are there? 3 combinations are there. So this we call it as threefold degenerate energy level. The degree of degeneracy, threefold. The degree of degeneracy is threefold degenerate energy levels. Now this is the next highest level. Now next is excited state 2. Okay, here combination what we took 2, 2, 1. Okay, now see, after 6, what we must get generally? 7, 8 in such a way. But directly we wrote 9E. Okay, in this 9E combination, this sets how we wrote means here we got 9, no? The next highest energy level will be 9 only. Why 9? I will explain. First, let us see how we wrote the combination. How we wrote the combination means 2 square plus 2 square plus 1. Okay. So, 2 square plus 2 square plus 1. 4 plus 4 plus 1. 8 plus 1, 9. Okay. In these three sets, if I write 1, 2, 2 also I will get 9. 2, 1, 2 also I will get 9. So these particular three sets are having same energy level of 9E. Okay, this we call threefold degenerate energy level. Then what about this 7 and 8? You may think. Now see, quantum number nx, ny, nz, no? Okay, now first for 6, what combination I took? 1 I am showing you. 2, 1, 1 combination I. Right? Now I want 7. 7 means how to write. Let us check now. If I write, how I will get 7? 2 square plus 4. If I write another 2 square, 4 plus 4, 8 I am getting. I can't get 7 in this combination if I write 2, 2, 1. Okay, if I write 1, I am getting 9 or no. Now next, or how could we write 2, 1, 0. If I write that 2 square 4 plus 1, 5 I am getting. But the last one you see, 0, no? Last one you see, 0. Whether quantum number will be 0. So this combination is not allowed. See, after 3, we wrote 6. 5 is not possible. Why 5 is not possible? Because one of the quantum number we have to take as 0. Here, see, this combination gives 5, no? 2, 1, 0 combination gives 5. But quantum number cannot be 0, no? So this is not possible. Next, after 3, 4 at least it has to come, no? But why we are not writing 4? See here, for writing 4, what you want? 1, 1, 1 combination, we are getting 3, so we cannot write. Now, 2 combination, 2, 1, 0. I am getting 5. So, how to write? 2, 0, 0. 2 square, for getting 4. 2 square plus 0 plus 0. But quantum number will be 0. Here we are getting the 4 value. But we have to take 2 quantum numbers as 0, which is impossible. So, after 3, what will be the next energy highest level? 6. After 6, 9. After 9, what we must get? 10 we must get, no? But I wrote 11. 11E. 10 we must get, no? So, 11. So, now here, for 9, what we wrote? This combination we wrote. Okay. Now, for example, if I write 2, 2, 2, this we call non-degenerate. Right? So, now here, I'm taking 3, 1, 0. What will be 3 square? 9 plus 1. But here, for 10, we have to take one of the quantum number as 0. Is it possible? No. So, following this, the next energy level, 3, 1, 1. 9 plus 1 plus 1, 11. Next, 12. Now, in these three combinations, we will get 11. Now, this is also threefold. Next, 12. 2, 2, 2. 4 plus 4 plus 4. 12. Non-degenerate. Unique, no? Unique set. Next, 13 we cannot get because one of the quantum number we have to take as 0, which is impossible. So, next higher energy level, 14. Next, 17. Next, 18. Next, 19. Next, 21. And for 14, 1, 3, 2 combination. For this 3, 2, 2 combination. For this 4, 1, 1 combination. Now here 14 you see. 1, 2, 3, 4, 5, 6 combinations. 6 sets we took. So this is 6-fold degenerate energy level. 17 3-fold, 18 3-fold, 19 3-fold, 21. These 6 sets gives 21E. So 6-fold degenerate. Okay, in such a way, we will write the energy levels of a particle in cubical box. Clear? Now let us go for the next topic. Okay, so first ground state, 1, 1, 1 quantum numbers. 4, 5 we cannot write. Because if we want to write 4, 5, one of the quantum number must be taken as 0, which is impossible. So the next higher energy level will be 6. Like that only we wrote. And this sets how we wrote means these particular sets gives the value 6. And these particular sets 6 are here gives the value of 14. You do nx square plus ny square plus nz square. You will get 14 for these 6 different sets. Okay. Now next, let us go for 3-dimensional harmonic oscillator. For isotropic oscillator, energy is n plus 3 by 2 h cut omega. Degree of degeneracy half n plus 1 n plus 2. Angular momentum Lx, L along x, y, z directions. Lx minus I h cut y dou by dou z minus z dou by dou y. Ly minus I h cut z dou by dou x minus x dou by dou z. Lz minus I h cut x dou by dou y minus y dou by dou x. Now, in terms of spherical polar coordinates, important bits, practice it in. First, Lx, I h cut sin pi dou by dou theta plus cot theta cos pi dou by 2 pi. Ly, I h cut instead of sin minus cos pi dou by dou theta plus cot theta as it is instead of cos pi sin pi dou by dou pi. One you practice perfectly, no? Logically write the opposite terms. Next, Lz minus I h cut dou by dou pi. Right? Now L square minus h cut square r square del square del operator I dou by dou x plus j dou by dou y plus k dou by dou z. What is the del operator? I dou by dou x plus j dou by dou y plus k dou by dou z. This we call del operator. Now del square minus 1 by r square dou by dou r square dou by dou r. Eigenvalues of L square. L of L plus 1 h cut square. Lz m h cut. For L square, this is L of L plus 1 h cut square. For L2, m h cut. Now commutation relations. The relation between x and y, Lx, Ly is equal to I h cut Lz. Ly, Lz, I h cut Lx. Lz, Ly, I h cut Ly. Logically, you can remember, no, x, y, here z. Y, z, here x. Z, x, here y. I h cut. Logically, we have to learn. Everything we cannot. So, some logically we have to remember. It will be useful for us. Next, L square, Lx is equal to L square, Ly is equal to L square, Lz. Commutative relations will be equal to 0. You have to remember that. Not 1. It is 0. Angular momentum. In general, first light. What is angular momentum? Angular momentum quantum number means the summation of spin momentum number, orbital quantum number plus spin quantum number. L plus S. J square. Jx square plus jy square plus jz square. L is orbital quantum number. S is spin quantum number. J is angular quantum number. Remember that. Ladder operators. Remember this, no? He will ask this combination and ask the answer. J plus angular momentums related to angular momentums. We call ladder operators. J plus Jx plus Ijy. J minus Jx minus Ijy. Jz comma J plus is equal to h cut J plus. Jz comma Ji minus h cut J minus. J plus J minus 2 h cut J set. J square J plus J square J minus is equal to 0. Right? Now next, spin angular momentum. Okay. A particle having intrinsic, that is spin angular momentum, S, we denote with S, which is unrelated to its orbital motion, is S comma L equal to 0. Okay. This S square spin angular momentum, this symbol you are seeing, no? This we call it as Dirac-Ket. So Dirac-Ket of SMS, we write as S of S plus 1 h cut square Dirac-Ket SMS. SZ Dirac-Ket SMS is equal to MS h cut square Dirac-Ket of SMS. MS means S comma S minus 1, so on up to minus 1. And the values of MS will be 2S plus 1. Now MS for S and 2S plus 1 states. For example, if S is equal to 1, MS, the S values are 1 by 2 and MS values are 1 by 2 minus 1 by 2. Now let us take this possibility values or possibility states, we can say 2S plus 1. In place of S, I am substituting 1 by 2 plus 1. That is equal to 2 I will get. If I substitute this half also, 2 I will get. Means 2 possible states are there. Okay. For the spinning. Okay. Now, of a particle. Now, Dirac-Ket S comma MS, we write it as 1 by 2, 1 by 2. Two combinations are no, 1 by 2, 1 by 2. Again 1 by 2 minus 1 by 2. This we say alpha state. Up spin will be there 1, 0. The wave function of MS. Alpha is the wave function of MS. Right? Now next, we are taking the combination of half minus 1 by 2. We call beta state. Beta stands for MS equal to minus half. This is downspin. It indicates downspin. It indicates downspin. So 0, 1. Beta value I wrote 0, 1. Okay. It indicates MS values. Alpha indicates wave function of MS. Right. Now next, general wave equation. Dirac-Ket X is equal to AB. That is equal to A 1, 0 plus B 0, 1. The general wave function. A, what is the A? Probability amplitude that particle has spin up. B, particle has spin down. So S is equal to half h cut sigma. Sigma means Pauli matrix. So the Pauli matrices, let us write now. Sigma X 0, 1, 1, 0. Sigma Y 0 minus I 0. Sigma Z 1, 0, 0 minus 1. Once he asked in set the Pauli matrices. Remember this. Next, S plus Sx plus Isy. S minus Sx minus Isy. S plus value half h cut sigma. Okay, sigma plus. That is h cut by 2. What is sigma plus? Sigma x. In this terms only I am writing. Sigma x plus I sigma y. H cut by 2. What is sigma x? 0, 1, 1, 0. What is sigma y? Here I know. Actually, I of 0 minus I 0. So, I becomes 1 and now I took common. Okay, 0, 1 minus 1, 0. So, now add it. 0 plus 0, 1 plus 1, 2. 1 plus minus 1, 0. 0 plus 0, 0. So, 2 I am taking common. 2 strikes off. So, h cut 0, 1, 0, 0. This we call rising operator. Okay. Now, lowering operator, sigma minus. Sigma minus means here what you will substitute? h cut by 2 sigma x minus I sigma y. Same values in a same procedure if we do, we get 0, 0, 1, 0. We call it as lowering operator. Some properties of Pauli's spin matrix. This is important. Remember, sigma x square equal to sigma y square equal to sigma z square equal to 1. Sigma cube is 3. Sigma x, sigma y equal to minus sigma y, sigma x is equal to I sigma z. Now next, sigma plus whole square equal to sigma minus square equal to 0. Sigma plus sigma minus is equal to 2, 1 plus sigma z. Already here we discussed the Pauli matrices, the value of sigma x, sigma y, sigma z, no? That we will substitute in the problems. Sigma dot A, sigma dot B equal to A dot B plus I sigma A dot A cross B. Now this is also the important Born approximation, the scattering amplitude formula. F of theta comma pi equal to minus mu by h cut square integral v of r e to the power of I k dot r dr. Now differential scattering cross section sigma theta equal to f of theta whole square. So this is minus 1 by k integral 0 to infinity r sin kr v of r dr whole square. Now lastly, some Dirac matrices. Dirac Hamiltonian generally written as h bar equal to c alpha bar into p bar plus beta mc square. The value of alpha x 0, sigma x, 0. Alpha y 0, sigma y, 0. Alpha z 0, sigma z, 0. So now here this can be written as 0, 0, 0, 1, 0, 0, 1, 0, 0, 1, 0, 1. See, diagonals are 1. Here the diagonal is alternate I minus I, I minus I. Now here this diagonals 1, 1, minus 1, minus 1, the beta value. Right? Now this is about the part 2. Some formulas we discussed. In the next video, some problems related to the quantum mechanics. Let us discuss. And then some practice bits. These problems also nothing but comes under the practice bits only. Okay. They may ask in the exam. So in part 3, let us discuss about some problems related to this chapter. Okay. So practice this energy level of a cubical box. Now these formulas many times he repeated. Okay, that is angular momentum, spherical polar coordinates, commutation relations. Now angular momentum in general. Okay. Now next the formulas, this energy level formulas he repeated many times. He will ask the formula he will say what is the formula for eigenvalues of energy, and he will give the formula in the option. You have to write down that particular formula. Okay, 0 point energy. Right? So, and also you be perfect with this 3 condition: orthogonality function condition, normalization, orthonormality condition for one-dimensional consideration of Schrodinger equation 1. So, if you like my video, please share it, subscribe it. Don't forget to press the bell. So whenever I keep the video, you will get the notification. Thank you for watching my video. Yours, Reshma Physics.